Okay, section 1.4, metabolic pathways and the chaining of reactions. Metabolic pathways are a collection of reactions that occur in a series where the product of one reaction is the starting reactant for the next reaction. So we can see here that the starting molecule is A and the end product of this pathway is F, and that all the in-between B, C, D, and E are intermediate products. And you have a number of reactions. You have A goes to B, that's one reaction. B goes to C is another reaction. C goes to D is another reaction. And D goes to E is another reaction, and E goes to F is another reaction. And each reaction has its own enzyme that's catalyzing it, and the product of each reaction is the reactant for the next reaction. Not all reactions in a metabolic pathway are favorable. Frequently, most are unfavorable. So what that is telling you is that, for example, I could have A goes to B, and actually under cellular conditions, cellular concentrations of A and B, and just the favorability of the reaction, its delta G standard, that this reaction actually favors the reverse process. And the same thing from B goes to C. And C goes to D. And D goes to E also. And then we'll leave this last part blank for right now, so we get to the next point. If most reactions are unfavorable, how does the metabolic pathway achieve its goal of producing the final product? Because the goal of any metabolic pathway is to produce the final product. And how you do that, usually the final reaction in the pathway is very favorable. So I'm putting a single arrow. When all the other reactions have double arrows, and then all of a sudden one of the reactions has a single arrow, that means that that end reaction, for example, E to F, is very favorable. So if I were going to write out the delta G's, or the delta G standards, for example, I can say the delta G standard for A to B is greater than 0. The delta G standard for B to C is greater than 0. C to D is greater than 0. And D to E is greater than 0. But this last reaction, E to F, the delta G standard is much less than 0. So what will that do? Well, when we have a situation like this, none of the reactions can reach equilibrium because of this last one. So the reaction A to B, or B to C, or C to D, or D to E, none of these reactions can reach equilibrium because the last reaction is removing all of E. It's very favorable. All of E will be turned into F. So if all of E gets turned into F, then reaction D to E cannot reach equilibrium because E is constantly being removed. So that reaction needs to take more D and turn it into E so that it can get to equilibrium. Well, if D is being transformed into E constantly, then the concentration of D keeps decreasing. So the reaction C to D cannot reach equilibrium. So it needs to take more C and transform into D so that it can get to equilibrium, and so on. So the last reaction, this favorable reaction, E to F, kind of pushes all the other reactants, starting with A and all the intermediate products, and makes all these other reactions have to move forward. So even though the delta G standards for all the reactions A to B, B to C, C to D, D to E are greater than 0, because of this last reaction E to F having a delta G standard much less than 0, that last reaction is going to pull all the reactants through. So as long as E to F, that reaction is functional, meaning that the enzyme is on and the reaction is proceeding, then the delta G for these reactions, the other reactions, will all be less than 0. And we'll see an example of this shortly. Negative and positive feedback in metabolic pathways. So we're just going to draw a metabolic pathway where the arrows are not representative of the favorability of the reactions. They're just showing you the pathway. So A goes to B, B goes to C, C goes to D, and D goes to E. And each one of these has an enzyme. Now, it could be that the final product E will come back and inhibit the enzyme that's actually catalyzing the transformation of D to E. And this negative feedback, as the concentration of E increases, this inhibition of enzyme 4, typically it's done through non-competitive inhibition. As the concentration of E goes up, enzyme 4 starts to get inhibited, and if the enzyme is inhibited, then this reaction is no longer occurring. So basically, you're stopping the reaction D to E. If D to E is no longer happening, all the rest of these reactions, if they are not very favorable, meaning that they have a delta G standard that is somewhat near zero, maybe a little bit less, maybe a little bit more, then these reactions will also quickly reach equilibrium. And what is equilibrium? That is simply nothing happening, right? Because the reaction is moving in the forward and the reverse direction at the same rate. So by inhibiting one enzyme in the pathway, you can inhibit all the other reactions also without needing to inhibit all the other enzymes. Again, we'll see an example of this shortly. So coupling reactions and activated carriers. So the first thing I want to say about this figure, I would like you to just ignore this, because I think these two statements right here are more confusing than helpful. So just ignore that part. Don't pay attention to it at all. Imagine that it does not exist, okay? The rest of the figure is fine. Free energy of Y is greater than the free energy of X, therefore delta G is less than 0, and the disorder of the universe is increasing during the reaction Y goes to X. So in this case, Y goes to X is a delta G less than 0. This is not the delta G standard. So it favors the forward reaction, and that will happen spontaneously. The reaction will move toward equilibrium by transforming Y into X, right? Now the reverse reaction of X goes to Y would have a delta G that is greater than 0. Imagine that the cell actually needs to turn X into Y. You need this reaction to happen. Well, this reaction cannot happen in this direction spontaneously because you're moving further away from equilibrium. The reverse reaction is the one that is actually moving towards equilibrium. So, in this case, what you need to do is you need to couple one reaction with another. And this is different than what we saw above with chaining reactions together. There are many reactions that are unfavorable but must occur. Protein synthesis, DNA and RNA synthesis, glycogen synthesis, and many more. Basically, any condensation reaction, because all condensation reactions in the cell are unfavorable. So how do you couple? The basic idea of coupling is that you have one reaction that favors the forward process, meaning that it has a delta G less than 0, so a negative delta G, and you have another one that has a positive delta G, and this is the one that you're moving away from equilibrium, right? So you couple them together where when you add the two delta G's together, overall you get a negative delta G. It could be that one reaction is a chemical reaction and the other one is some sort of physical reaction. So I have an example here to showcase that and what that means. So we're using delta G's on the right hand side because in most cases, and almost all cases, in the cell you're not going to have equal concentrations of product and reactant. So under cellular conditions, you'll always be away from standard conditions, so delta G is a better representation. What delta G standard tells you is whether at equilibrium you're going to have more product than reactant, right? So here we go. We have one reaction here, AOH plus HB gives you AbH2O. So this is a condensation reaction. So let's just give it a big C here for a condensation reaction. Now this has a delta G that is greater than 0. We'll mark it with red underneath to say, okay, this is a delta G greater than 0. This reaction actually does not favor the forward reaction. It favors the reverse. Now we're going to look at the second reaction, number 2. A phosphorylated plus HB gives me AB plus inorganic phosphate, And this is not a condensation reaction because you don't have H2O as an output. And this actually has a delta G that is less than 0. So this actually does favor the forward process. But the problem is to phosphorylate A with an inorganic phosphate right here. This is also a condensation reaction because you have H2O as an output, and this does not favor the forward process because you have a delta G greater than 0. So this cannot happen. So the two reactions that have a delta G greater than 0, you're actually moving further away from equilibrium. So now, how do you generate A phosphorylated? Well, ATP hydrolysis is a very favorable reaction. All hydrolysis reactions are favorable, but ATP hydrolysis is even more favorable than normal. Okay, we have a delta G much less than 0, and just to make sure that this is a condensation reaction up here. So we know that this can easily happen, but so what? Well, you can couple these two reactions together where you have the AOH plus the inorganic phosphate going to A phosphorylated plus H2O, which has a delta G greater than 0 right here, to the ATP hydrolysis right here. And when you add up the delta G's, you get a delta G less than 0. And right here, you can see that I put all the reactants on one side and all the products on another. Now what you do is you remove what the reactant side has in common with the product side. So if we look, H2O goes away. And what else do I have? 2 inorganic phosphates go away. And when I then rewrite it, I have this. AOH plus ATP goes to A phosphorylated plus ADP, and this has a delta G less than 0. So what we did was we solved this problem that we had up here, which was phosphorylating A, right? But now that we phosphorylated A by coupling it to ATP hydrolysis, then we can simply use this reaction right here to attach A to B and get our AB molecule, which are A and B covalently attached to each other. So how does coupling occur? So the coupling of reactions 3 and 4 occur at the active site of an enzyme and have the appearance of occurring simultaneously. This coordination occurs seamlessly and very quickly, giving the appearance that a single reaction has occurred. So a single reaction has not occurred, but it seems that way because the enzyme is just doing such a fantastic job. Okay guys, we'll stop here and continue later. Thank you.